phenomena called free boundary problem solutions, which often of late people are talking. So can you throw some light on this?
Okay, yeah. Oh, it's so nice to again meet here, Raman. I thought that I was to skip this time, but still somehow we had some time to meet, and we were also trying to get ourselves ready with tomorrow's flight.
Okay.
Yeah. And then, anyway, nice that, after all, what really matters at the end of the day is how best professionals like us, in the community of mathematicians, or for that matter, any intellectual exchange of ideas. So some good time is, one can welcome these things, okay? Yeah, free boundary problems. I have heard about these things, but let me put it this way. Before I look at some of these problems, very interesting one, that's a very interesting inquisitive question too at the same time. If you are a student of topology, you would know. Okay, a topological space, when we were introduced for the first time in our undergrad courses in mathematics. So my teacher gave one course on topology. Then it was so, I was a bit aghast. At the same time, I was also confused. And slowly, I tried to appreciate the idea of putting a topology in a set and then bringing some exciting algebraic ideas and then arithmetic ideas, the entire calculus ideas into.
But you want to lead into domains, interior points.
Yeah, exactly. So when I say that it's a topological space, in those days it used to be a point set topology. Okay. I mean, now also in most of the university departments they are given a course on point set topology. Yeah. And people are now. At one time there were hours to this. That the students are missing the main thing. Yeah. So one need to look at the real interesting things like rule-dimensional topology and etc. and all that. Again, point set topology is coming back there.
Okay.
Then we talk about interior points, exterior points, and the boundary points. So we demarcate a domain, and naturally, when it separates the given space into two parts, so some of the points that lie in one domain, they constitute interior points, they say something. And then exterior points are those which are complementary to these interior points in the language of set theory as well. Yeah. And then the boundary that is common to both these points, which are there, some of them as interior points and some are thrown out of it. And then there is a boundaries down here. Those points they are also called as frontier points, which are neither interior nor exterior points. The boundary, we heard about these things.
Yeah, but in the context of PDEs, like in the natural setting.
Yeah, and these great ideas. So the idea was to develop analysis, and more so a mathematical analysis, which we were introduced to on real line, the mathematical analysis on R and C, etc., which are also in their own way, naturally, they were also topological spaces. All right, and so when they introduced, they wanted that all these theories can be developed on abstract topological space. So in that sense, it was more so of a calculus course than anything else. So when we say calculus, our interest was to solve a differential equation. Okay, if it is ordinary differential equation is one thing, and then naturally when we look at most of the things in nature, they come up as partial differential equations. Yeah. And therefore...
yeah, I understand something like the wave equation or heat equation.
Yeah, we talk about wave equation as you said, and then sound propagation, and heat equation, and then some metallic thing is heated, and then they would like to to see how the heat
Evolves.
transmits,
Yeah.
and then heat and mass transfer, as the physics people, engineering people talk about all those things. But mathematics would take in a more general sense, they want to put it abstractly, so that these cases would become particular cases.
But they talk of one very concrete problem defined by so-called the Stephen's law. Stephen's
Yeah, I heard about these things. The free boundary problems, as you were trying to refer in the beginning. I think you must have observed. So when you go to so the places like Himalayas, in India, that is
Glaciers
the only
melt,
place.
causing sea
If you
levels
want
to rise.
visit someone,
But not
they
all
want
of
to
that
go
melt
to
happens
the
at the surface.
points, like,
In the summertime,
so the frozen
rivers and
ice
pools of
lakes and all
meltwater
these
find their
things.
way down through the glacier to the bed below. From there, the water...
Can these kinds of phenomena that we see in nature, like
model.
water melting itself into ice, becoming frozen, gets freeze and becomes ice, and then ice then melts, and then this exchange of forms of water and then solidification can be said as, some partial differential equation has to come into this picture, and then the boundary seems to be common to both medium. So one is a liquid water medium, fluid, the other one is solidified one. But at some common portion, the interface between these two domains, we see that the ice lump is melting. So
but in the
that
process,
boundary allows you to happen.
okay.
At one point of time, if it freezes means the boundary allows freezing to happen. If boundary doesn't allow certain things to happen, as you see in heat equation, we insulate the boundary. So that no heat can go out of the body, or it can entertain any external heat element to get into this body. So this is the thermal kind of conditioning. So in those cases, those boundaries are not anymore free.
But in this particular example, a priori we do not know.
We do not know
the demarcation.
But the demarcation, and it seems that such problems involves determining one or more unknowns. Okay, and then the laws, it has to respect those laws. So the PD is related to ice formation is one kind of medium that you have.
And therefore, this climate change theorists
should
look at these problems.
Flame propagation, for example, the forests catch fire.
I want to know more about this flame.
This is a flame. See, same thing. See, what I would say is, if we cannot handle this problem, then the nature has its own mechanism to find solutions. It can
in the context of fire.
Fire, So fire breaks out, and then after some time, on its own it doses up. It doses up because there is a free boundary kind of a thing. So dose up means from one form to the other form. It has to die down. So this is exactly dying down kind of a thing. Where there in case of ice plump, it melts. Dying down in the sense it changes their form. Sound waves, for example, after some distance, I don't hear sound. They die down. So wherever you see, and nowadays even people talk about free boundary problems even in financial mathematics. Optimal stopping times is another area. See, look at it from climate change, from natural phenomena. They give a lot of motivation for us to model these kinds of problems. I suppose there must be many more. I'm sure you would agree with me. But I'm told that in the 50s till 70s, these were the leading PD people like Relax and so all these people, Levy. So there is the Levy process. We heard about those things. They talk about see, if you put everything on a probabilistic way of looking at the things, where when I said that optimal stopping times, probably in a financial markets kind of thing, volatility is one thing that really.
What are the big names, if you can think about, like Luis Caffarelli is still working on these kind of problems?
Maybe, maybe afterwards I think, when these people initiated in 50s and 60s, they were basically, I was told about water waves kind
Yeah,
of.
yeah.
Okay. And then the point is, two-dimensional, three-dimensional things.
Okay.
You look at the free flow of water surface.
Yeah.
Okay. So the fluid is three-dimensional,
Yeah.
but the interface is a hard river bed kind of a thing.
Yeah.
Okay. And now you see, a lot of water evaporates,
Yeah.
goes into atmosphere.
Correct.
And then again, there is water cycles.
Yeah. We can see so many examples in this setting.
Exactly. Yeah.
Nice, I think.
Yeah.